Alrighty, so I'm going to get started. Announcements for today. Chapter 15, Sapling, is due 9 a.m. Monday next week because I'm going to finish it up today. Chapter 16, I'll open this afternoon, and the notes for that are already posted. I may or may not get into that today. Also, we have an exam coming up Tuesday night next week, 7 to 9 p.m., and it's in Chem 140. That's actually for both OChem 2 lectures combined, so we need a bigger room than this. And then finally, I guess those of you who took OChem 1 with me, I usually do an exam review session like the weekend before the exam at some point. Usually Sunday afternoon or evening tends to work best for people just because that's giving them like Friday and Saturday to look at the material and come up with questions or figure out what they need to go over. Well, I guess, let me ask it like this. If I did say like 2 p.m., like mid-afternoon on Sunday next week, would that work for people? Like, okay. Is there anyone who like wants to make it to an exam review Sunday mid-afternoon and cannot? Okay. If I did lecture capture, would that? Okay, cool. I'm going to make sure that I push people to get it set up early this time because I know in the past I promised that on 1 or 2 review sessions and then it ended up not happening, but I'll let you guys know once I get the room details sorted out, and then I can set up the auto capture thing through OIT. But let's tentatively plan on 2 p.m. Sunday. Assuming I can get a room. And I'll let you guys know how that ends up panning out. Okay, so I'll include this in the email, but the gist of how I do exam review sessions is I don't have any material planned in advance. I pretty much show up and say, okay, hit me, what questions you got? And then we can just spend a while going over either like questions from Sapling or the textbook or the exam archives, or like if you have more general questions of like, I still don't understand how this concept works, or what would happen if you did this in this setting. Pretty much just anything you guys want to go over, we can look at in preparation for the exam. Oh, and I guess exam, by the way, it's listed in the syllabus, but covering chapters 14 through 16 is fair game on the exam. And I'm planning on doing the last little bit of chapter 16, probably the Monday, the day before the exam. So that is like a little bit of a short reaction time, but most of 16 will be covered the week before that. So the end of 16 is kind of like putting together multiple things from earlier in the chapter. So there's some new material in there, but mostly the early stuff in 16 is kind of the more important to know. Okay, questions about, yeah?
So Sapling covered some of the mechanisms and reactions from OChem 1.
Mm-hmm.
Is this going to be applicable on our exam? There's like certain ones that you know we should know, or if they were explicitly covered by you, like
so I guess like the ones I explicitly covered in lecture, like especially in the context of 14, where I'm like, here's sort of something similar to OChem 1, but now we're doing it to alkynes, that's definitely fair game. Oxymercuration for alkynes I will not cover, and I know there's a question about that on Sapling, which I had in from the last time I taught this and decided to pull that topic out and then didn't pull out of the sapling, so my bad on that, but I'm not going to ask you about that because it's kind of not really known for sure. So oxymercuration's out. But yeah, in general, I'm not going to ask questions that are specifically like you could answer them fresh out of OChem 1 without having seen any of OChem 2, but I might be like, here's something you could do with an alkyne that's like similar to acid-base stuff that we've covered before, or like ties into things that you should know from OChem 1 kind of. And I guess it's always possible for it to pop up on syntheses, of course, too. But I guess in terms of focusing your studying, probably the best place to start is, if you're looking at reviewing OChem 1, I mean, maybe know the overall reactions, and then any mechanisms that we're going to use as fair game will be ones that I've covered or reviewed in lecture from stuff that we did in the past. So. Okay, any other questions about that? Okay, cool. Alrighty, so today I'm going to wrap up 15, and the last couple of lectures we did reactions specific to dienes. So, given that the chapter is called Dienes and Aromaticity, guess what we're getting into today? So, okay, so we've sort of been seeing hints of aromatic ring behavior a little bit in the past. We treat aromatic rings as sort of their own category of hydrocarbons. And so far, we've been treating benzene as kind of the be-all, end-all of aromatic rings. So benzene is this six-membered ring with alternating single and double bonds. And it can do resonance, where you rotate all of the double bonds around the ring. And actually, if you look at the arrow pushing for this, kind of a side note that's cool, this is actually the same arrow pushing that you used to show Diels-Alder happening. It's like a 6-atom transition state where all of the pi bonds click around the ring at once. The difference is in Diels-Alder, we're actually forming some new sigma bonds. Here we're just keeping the sigma bond framework the same and pushing some pi bonds around a bit. Okay, so we can show it with the pi bonds either in like these locations or these locations, and those are in resonance to each other. So we can just sort of average the whole thing together to a 6-membered ring with a circle in the middle. And the more of these I draw, the more that's going to look like a donut, but that's kind of what we're going for here. And that's just to say that on average, all of the bonds around the ring are going to be 1.5 bonds. For every carbon-carbon bond. So they're all equivalent to each other. The ring's symmetrical overall. Okay, so these are kind of their own category of hydrocarbons. They don't do any of the stuff that alkanes or alkenes or alkynes do. They're totally different in chemical behavior. So when we saw alkene reactions in chapters 4 and 5, we had a side note of benzene doesn't do any of this stuff. It's not really considered an alkene because once you get that ring going, something changes and it's a totally different beast now. Okay, so we're going to spend a while looking at aromatic rings and also learning that benzene is the most common example in this category, but there's actually a ton of other ways that you can get aromaticity going on. Okay, so conditions that something needs to be aromatic. So conditions for aromaticity. First thing is that it needs to be cyclic. It's got to be a ring. The second is that it needs to be flat in a single plane. So we're going to see some cases where that happens not to be the case. But in general, we're going to start out assuming that things are planar until we have some reason to believe otherwise. Okay, and we'll cover some examples of how to tell on that one. Okay, so those are pretty easy to pick out or determine. The third one is a little bit more involved. So what we're looking at here is every atom around the ring has to have some involvement in the pi system. So in other words, it has to have an unhybridized p orbital. Okay, so a few different ways you can get this going. For instance, in benzene itself, that p orbital is tied up in a pi bond in the case of all 6 atoms. Okay. So it can have a pi bond to get into the pi system, or it can have a lone pair. So long as the lone pair happens to be perpendicular to the ring, we can evaluate how to figure that out in a little bit here. So a lone pair in a p orbital would count. And on carbon, most commonly, that's going to show up in the form of a negative charge. Although if it's some atom that has a lone pair like by default, like say oxygen or nitrogen, it might not have a charge on it. Or it could be in the form of an empty p orbital. Which on carbon is generally going to show up as a plus charge, because we know carbocations have an unhybridized p orbital. Okay. So in other words, because every atom has to have some unhybridized p orbital, at least one, every atom around the ring has to be generally sp2 hybridized, although you can do it. Yeah, I don't think we're going to see any cases of that. But yeah, every atom around the ring is generally going to be sp2 hybridized. Okay. So if we're meeting these 3 criteria, then we can go in and check how many electrons are actually involved in the pi system altogether. So if the above 3 conditions are met, we're going to count the electrons in the pi system. So this is like all the electrons in the pi bonds, all the electrons in the lone pairs. We're going to add them all up. And there's 2 possibilities that we're likely to see. If it fits the pattern of 4n electrons, and n can be any integer, so I'll do some examples in a second. This is called anti-aromatic, which means that it's much less stable than it would be otherwise. If it happens to fit the pattern of 4n plus 2 electrons, then it's aromatic, which means it's more stable. Okay, so some examples. So n is pretty much whatever integer you want, and it honestly doesn't matter what it is. This is just a way of us saying that numbers that fit this pattern are like 2, 6, 10, 14, 18, whatever. Honestly, it doesn't matter so long as it's one of the numbers that falls into that sequence. Meanwhile, 4n, the bad numbers, are like 4, 8, 12, 16, so on. Doesn't matter which one of that sequence they are, but all of them are bad for stability. Okay. So the reasons why these numbers are good and bad for stability basically comes down to MO kind of energy levels. If you're curious, the reasoning behind that, the book has kind of an explanation of frost circles that you can use to determine orbital levels, but I think I'm going to skip over that in terms of sort of really digging down into the explanation and spend more time on how to identify aromaticity and anti-aromaticity. And then in the next chapter, we can deal with what to do once you have it. Okay, so one more thing about this. This is called the Huckle 4n+2 rule. So this guy figured out that if you've got an electron count that falls into this pattern, stability is going to be way higher than you would expect for that type of alkene. Question? Any integer, doesn't matter what. So pretty much like if you plug in 0, then you get 2. If you plug in 1, you get 6. If you plug in 2, you get 10. And n like itself is totally meaningless and irrelevant. It's just kind of a way of generating that pattern. So, Okay, other questions about that? Okay, cool. So let's look at some examples of how to tell. Oh, and I guess one last thing that I didn't mention here is if any of conditions 1 through 3 are not met, then it's non-aromatic, which is not the same thing as anti-aromatic. Okay, so non-aromatic just means the same stability as you would expect for, whatever alkenes that you have in the molecule. So there's nothing happening to destabilize or stabilize it. So same stability as expected. Okay, so basically we've got 3 possible outcomes looking at these structures. Either it's like 0 sum or 0 change, in which case it's non-aromatic, like the default, or we could be getting some good stabilization, which would make it aromatic, or some destabilization, which makes it anti-aromatic. So let's go through and look at some cases of all of these. Okay, so I'm going to be drawing some 7-membered rings here. Easiest way to draw these is start out doing one side looking like it's going to be a 6-membered ring, and then like fold it outwards a little bit and then do sort of a peak on one side is how I normally draw them. Okay, so I'm just going to draw up 3 examples here real quick and then we can talk about all of them. Okay, and they're all 7-membered rings. Okay, so let's look at all 3 of these things. Okay, so first criteria, all of them are cyclic, so check. Second criteria, we don't know for sure either way, so we're going to start out assuming that all 3 are planar. If that turns out to be bad for stability, then the molecule might sort of finagle its way around by breaking that rule. And then we want to check every atom in the ring must have a p orbital perpendicular to ring. So in other words, everything must be sp2 hybridized. All right, so here we've got 1, 2, 3, 4, 5, 6 atoms around the ring that all have a pi bond tie-in. But this one here, if we fill in the details on that carbon there, this one is actually sp3 hybridized, like it's all sigma bonds. And so that right there, I guess think of aromaticity as like a closed circuit running around the ring. And if you have any atom around the ring anywhere that breaks the continuous cycle of sp2 hybridized carbons, then that's going to sort of open the circuit and no aromaticity or anti-aromaticity is possible. Okay, so sp3 carbon is breaking aromaticity, so this one would be called non-aromatic. Okay, so this one is going to be exactly the stability you would expect for just a regular old cycloalkene, actually. Like, it's going to do just diene chemistry and alkene chemistry and like nothing particularly special about it at all, really. Okay, so let's move on to these two. All right, so they're both cyclic, they're both planar. This one, we want to check, does every atom have some involvement in the pi system? Again, we've got 6 atoms that are pi bonded to each other, so that checks out. And then here, we've got a carbon with an unhybridized p orbital. So, yep, everything does have some involvement in the pi system. Okay, cool. So we've checked out through rule 3 so far. Now we want to go through and count how many electrons are in here. So we've got 1, 2, 3, 4, 5, 6. So we're counting just the electrons from the pi bonds and from lone pairs. So 0 electrons in lone pairs. Actually, let me move that down so I'm out of the way here. Okay, so 6 electrons in pi bonds, none in the lone pairs. That puts me at 6 pi electrons total. And that's matching our pattern of one of the numbers in the Huckle 4n plus 2 rule. So this is going to be aromatic. Okay, so stability-wise, this is actually going to be much more stable, much less reactive than it would be if we didn't have the plus charge. So reactivity-wise, I guess what you could show this as is, well, I guess not if you start from here, but having a carbocation here on this carbon is actually much more stable than you would expect for any other carbocation, not just because of resonance, where you can like move the plus charge around the ring, but also because we've got this added boost on stability, where as soon as you form a carbocation here, suddenly you're accessing aromatic stability, and this is actually going to be much more willing to exist and sit around for a lot longer than a regular carbocation would be. Okay, so questions about this one? Okay, cool. So then let's look at the last one. Okay, we're planar, we're cyclic. Looking at this, every atom around the ring has some involvement in the pi system. Potentially. So here, so we can actually finagle this rule if it turns out that it's going to be bad for stability, but for now, let's assume, so if we assume lone pair is in a p orbital, and we'll cover how to determine whether or not that's the case sort of partway down the next page. So if we assume the lone pair is in the p orbital, and if we assume this is planar, which we still are, then we're meeting all 3 of the first 3 criteria. And that means that we have, for pi electrons, 1, 2, 3, 4, 5, 6, 7, 8 in the lone pair. So 6 electrons in the pi bonds, 2 electrons in lone pairs. And that puts us at 8 pi electrons total, which means that if both of those assumptions are true, then this is going to be anti-aromatic. Okay, So I'm sort of hedging my words quite a lot here because it turns out that the molecule really doesn't like being anti-aromatic at all. And so any wiggle room you give it to get out of being anti-aromatic, it's going to choose that and sort of avoid being anti-aromatic if it possibly can. So this actually has two different ways to do it. One is it could avoid it by not hybridizing its lone pairs into a p orbital. So we'll see a few more examples of this on other atoms, but on other molecules. But the lone pair on this atom, I guess if the molecule sort of realizes that it's going to be anti-aromatic, it can just say, right, I'm not playing this game anymore. I'm just going to break the rule 3 up here and take this atom out of the cycle entirely and break any chance of aromaticity or anti-aromaticity. So it can avoid that by putting a lone pair into sp3 orbital instead. Or the other option it has for sort of weaseling out of this is it can actually choose to fold up a little bit and become non-planar. Okay. All right. So questions about those before we do a bunch more examples? Yeah.
So by becoming non-planar, it's becoming non-aromatic rather than
Yeah, exactly. It's sort of opting out entirely because it realizes it's going to lose if it keeps trying to do aromaticity. And then, sorry, I think Michelle, I saw you first. Yeah. Sorry? So it's basically going to pick whichever one is best for the molecule if it has a choice. So if it comes down to like, it can either choose to be non-aromatic or aromatic, then it'll pick aromatic because aromatic's the best. But if it comes down to it can be either anti-aromatic or non-aromatic, then it's going to pick anti-aromatic. So we'll cover some examples of like where the molecule gets multiple choices, and it'll always pick which one is best for stability. So, okay, yeah.
by putting in an sp3, does that mean it's bonding to something else?
Not necessarily. So it's, let me actually draw an orbital kind of shape that's going on here. So, okay, and sorry, I saw a bunch of other hands, but let me draw this real quick and then I'll get back to questions. Okay, so say we're viewing one of these rings side on. I'll do this for benzene because it's a little bit easier to draw. Okay, so here's benzene. We got pi bonds. We got p orbitals. They're all perpendicular to the ring. And so we can like, basically what's happening is it's sort of making this continuous cycle of p orbital kind of things up on top of the ring. So it's kind of doing this donut-shaped orbital above the ring and then another one below the ring. So okay, so that's kind of how it looks on benzene. For this rightmost one here, okay, so you've got sort of the same thing here. All of the pi bonded atoms have their p orbitals. Oh, I gotta move the camera. Okay. And then if you choose to have the lone pair be in a p orbital, then it'll be perpendicular to the ring as well. But once we go through and do the math, that turns out to be really bad. So instead, it's going to choose to do like this sp3 kind of lobe sticking out to one side. So this atom here has nothing that's like above and below the ring anymore. It's just sort of like opting out. And that breaks the cycle of the continuous pi orbital above and below the ring and sends this into like the non-aromatic default category, if that makes sense. So it's basically if this atom chooses to be with an unhybridized p orbital, that tells us it would be sp2 hybridized. Here, it's putting everything in hybrid orbitals, so it's choosing to be sp3. And in the past, we've always treated lone pairs as if they're in sort of their own hybridized orbitals. So a carbanion we would have treated as like sp3. Turns out that they can choose to either put that lone pair into a p orbital or into a hybrid orbital, like an sp3 orbital, depending on what ends up being best for molecule stability overall. Okay. So I think, yeah.
So if it's always going to choose to be non-aromatic over anti-aromatic,
If it can finagle one of these rules, so like if it can tweak the hybridization of a lone pair or if it can fold up, that might not always be an option though. So we'll look at a few examples where it's pretty much stuck and forced to be anti-aromatic, whether it likes it or not. Okay. Sorry, I saw a couple other hands. Yeah.
So how does it form the sp3 if there's no other influence from another?
So it doesn't have to be influenced by another molecule. It turns out just the stability of aromaticity itself, or at least not being anti-aromatic, is enough to sort of, tip the balance in favor of one hybridization over the other. Yeah, so like, if it were not for the rest of this molecule, like if this were just like all single bonds and it were just this one atom in isolation, it would actually prefer to be sp3 hybridized just because that actually gets it in the lone pair orbital more s character and it's held in closer to the nucleus and more stable. So without the rest of the ring going on, having the lone pair be in a p orbital is actually not as good stability-wise, but it turns out that's kind of dwarfed by the huge, huge benefit you get from being aromatic, if that's an option. But it's also dwarfed by the huge disadvantage you get from being anti-aromatic if you're at risk of having that happen. So really, aromaticity or anti-aromaticity is going to be sort of the most important consideration over what an individual atom might happen to want, if that makes sense. Okay, so maybe let's do some more examples and then we can sort of look at what's going on with a few kind of opting in versus opting out of aromaticity. Okay, so going non-planar to avoid anti-aromaticity. Okay, so this is another option that rings have. All right, so I'm going to draw an 8-membered ring now. Okay, so this one we can check. It's cyclic. We assume planar for the time being. That might change as we realize what we're coming up against. And then every atom around the ring has some involvement in the pi system because they're all double bonded. If we do that, then we end up getting 8 pi electrons. Thanks. Okay, so 8 pi electrons means this thing is anti-aromatic. Okay, so again, this realizes it's going to lose in stability, so it's going to do whatever it can to break any of the previous rules here so it can just sort of pull itself out of the game entirely. Unfortunately, we can't tweak the hybridization of any lone pairs here because we don't have any. So instead, I'm going to switch chalks here. So we can't change lone pair hybridization, but we can change planarity. so even though we're showing this in the top-down view as kind of this like flat 8-membered ring, this thing is actually going to curl up into sort of like a boat cyclohexane looking thing, only it's 8-membered instead of 6. So I'm going to draw 2 lines parallel, and then I'm going to have sort of this like squarish flap sticking up on either side. Okay, and then when I fill in the double bonds, I can draw them here and here. Okay, so this molecule is called cyclooctatetraene. Which we could actually just figure out from what we know from chapter 4 already. It's cyclooctane, but it's got 4 alkenes in it. If you want, you could call it 1357 cyclooctatetraene, but it turns out there's really no other good location for those double bonds because you can't have them as cumulated double bonds. So cyclooctatetraene, or COT, curls up to avoid being anti-aromatic. Okay, so this is another way that it can opt out of the whole game and just say, no, I'm going to lose, so I'm just going to become non-aromatic instead. Okay, so one case where this is not an option, and I didn't include this specific example in the notes, but this one here, cyclobutadiene, has 4 pi electrons. That also puts it anti-aromatic. But this doesn't have as much flexibility as cyclooctatetraene does. It's a 4-membered ring. You can't really bend it at all. So this one is actually stuck being anti-aromatic. Okay, so cyclobutadiene is actually too unstable to exist at room temperature. I'm not sure, but I think some people might have made it where they like immediately trap it in some cold crystals of like frozen solid noble gas of some kind. But yeah, this thing is very unstable and pretty much can't exist for very long at all. Okay. So questions about those examples? Yeah.
Talking about becoming non-planar,
Mm-hmm.
is there a rule for what size the ring has to be?
So in general, it's, I think, larger than about 6 atoms is where it starts becoming a really solid option. So, and really, like, it's not a fully black and white issue either. The question is, like, can it flex enough to where, like, that orbital overlap that I have going on up there becomes not really an issue. But I think larger than 6 is generally considered, like, where it can flex enough that it's not really considered anti-aromatic anymore. Yeah.
Do you have to know how to draw the non-planar version of it?
No, just knowing enough that it'll flex non-planar is enough that you need, all that you need to know. So, and then sorry, yeah.
What does it become if it's so unstable that it doesn't want to go non-planar?
So, okay, so I guess branching off a little bit here. This thing, it turns out, is actually going to split up its pi bond so that instead of a pi bond there, it's going to do this diradical kind of thing. And looking at that, you're like, how does that even exist? That looks insanely unstable, and yeah, it is, but at least it's not anti-aromatic. So yeah, aromaticity is a lot of energy at stake. And so this thing can then go and do kind of radical chemistry on stuff. And so anything around that you put it with, like it might go find another copy of cyclobutadiene and react with that, or whatever else is around for it to react with. So, Okay, so other questions about these 2 examples before we get into ones with not carbon and hydrogen in them, or other atoms other than carbon and hydrogen? Okay, so we're going to look a little bit at aromatic heterocycles. Oh, sorry, question? No? Okay. So we know heteroatoms are anything other than C and H. So that's kind of what we're looking at here. Okay, so kind of like we showed up here, we can choose what hybridization we have on a heteroatom with a lone pair. And we can use that to sort of tweak whether we end up more or less stable. Okay. And I guess one thing I should mention here is sometimes we don't actually have the option of including the lone pair in the pi system. So sometimes we can't p hybridize, or I guess a better way to say that is sometimes we can't put the lone pair in p orbital. Usually that'll be the case if the atom that it's on is already involved in a pi bond, because in that case the tie-in to the pi system already exists on that atom. Okay, so let's walk through some examples here. Okay, so this thing, we've got a 5-membered ring, one atom of which is a nitrogen with a lone pair and a hydrogen on it. Sorry, question? Or, no? Okay, sorry. Okay, so it's cyclic. We're going to assume it's planar unless we have a good reason to believe otherwise. If we count the lone pair, so in other words, if this lone pair is tied into the pi system, then that gives us every atom on the ring has some tie-in to the pi system. And how many pi electrons would we have if the lone pair is involved? 6, yep. So if we count the lone pair, it's 6 pi electrons, so aromatic. If we don't count the lone pair, then we only have 4 electrons, but at that point it doesn't even matter because now we're breaking rule 3 and this atom is kind of not even part of the pi system in the first place. So so if we don't count the lone pair, then it's non-aromatic. So out of those two options, aromatic is better than non-aromatic. We're going to count the lone pair. So this is aromatic, and that also tells us that the hybridization of the nitrogen is going to be what? Yep, exactly. Okay, so because we're counting the lone pair, that means the lone pair is in a p orbital. So I guess, sorry, I should explicitly put that up here, but when I say count the lone pair, I mean the lone pair is in a p orbital. Okay, so if our lone pair is in a p orbital, the nitrogen has one unhybridized p orbital, which leaves it at sp2. Okay. Other examples. How much time I got? Okay. Yeah. Oh, yeah. Hi.
How can it be sp2 if it's bonded already to 3 things plus lone pair?
Yep, so the lone pair, we have some wiggle room on how to change the hybridization. I guess if you guys remember sort of, when did it come up? Like we were looking at nitrogen a few lectures back where it's got a lone pair and 3 things on it, and the lone pair can like go p hybridized real briefly and then like pop out the other side of the nitrogen. It can actually stay in the p hybridization, or stay in a p orbital permanently if that ends up sort of being the best outcome for the molecule. So lone pair here could be in a hybrid or it could be p, whichever one works out to give us the best outcome kind of. So it could be sp3 if that turned out to be best for the molecule, but it's not here. Okay, yeah.
So saying something's in the pi system is synonymous to saying it's sp2 hybridized.
Yes, for large rings, I guess. Just trying to think if you could do this with an sp hybridized atom. And I don't think the geometry works out. So yeah, I think it does have to be sp2 hybridized. Uh-huh.
Are you able to change the hybridization of the atoms and not aromatic?
Yes, so I guess that's kind of what we're doing with the, like this example over here, where it actually has 2 ways of opting out of anti-aromaticity. One is by tweaking the hybridization of the lone pair on this carbon, and the other is by going non-planar and avoiding it that way. And I'm actually not sure in real life which one it chooses. Maybe it's some combination of both, like whatever like the minimum of like the energy graph ends up being. But yeah, it doesn't matter if it's carbon or not, like it can still fiddle around with the hybridization on the lone pair. Yeah, good question, thanks. Okay, so here's one. And I guess you might recognize this from OChem 1 because that's pyridine. And we actually had that show up a few times like as a proton scavenger when we were doing tosyl formation or tosylation. Okay, so in this case, if we don't count the lone pair, well, hold on, let me back up a second. In this case, we cannot count the lone pair in the pi system because there just isn't room for it above and below the ring. This nitrogen is already part of a pi bond that's sort of occupying that space. So can't count the lone p because nitrogen is in a pi bond already. So if we don't count the lone pair, then every atom around the ring is still tied into a pi orbital, or into the pi system. So this gives us 6 pi electrons. So fortunately, everything works out. So it's aromatic. And then what's the hybridization of the nitrogen's lone pair? Yep. So we know that it's not in a p orbital. It's a hybrid orbital, but given that nitrogen already has a double bond going to it, the nitrogen itself, just based on what else is attached, was already sp2. Which the nitrogen is just going to put it into a hybrid orbital that matches what the nitrogen has going on in terms of hybridization already. So that nitrogen is already sp2 hybridized because of its double bond. All right, so this one you can sort of figure out just based on this more or less looks identical to benzene. It just happens to have a nitrogen there instead of a carbon. So we know that we don't actually need this lone pair to get aromatic because it's kind of superfluous. We already have all the requirements for aromaticity met just based on these 3 pi bonds around the ring. Okay, one more example. So here we have an oxygen with 2 lone pairs. So at first glance, we might think we could count all 8 electrons of those lone pairs. Turns out that's bad for 2 reasons. One is you just don't have room to get both lone pairs perpendicular to the ring at the same time. Only one can be in a p orbital and sort of match that geometry that I've shown up there. But So I guess it comes down to a choice between we count none of the lone pairs or we count one lone pair. So if neither lone pair is in the pi system, then it's non-aromatic. Because at that point it looks just the same as it did for this first example up here. We're breaking sort of the circuit around the ring. If one lone pair is included, then every atom around the ring has a tie-in to the pi system, and we have 6 pi electrons at that point. So it's aromatic. Okay, so this is kind of an interesting case because it turns out one of the lone pairs is part of the pi system and one is not. So the 2 lone pairs on that oxygen are actually totally different from each other chemically. Like one is sort of sticking out to the side. Let me just draw this edge on real quick. So one of the lone pairs is sticking above and below the ring, and the other is hanging out to the side. This one is too busy tied up in resonance or tied up in aromaticity in the ring to like do anything chemically. And then this one is free to go out and do chemistry with other stuff. Okay, so I didn't quite get to the synthesis problem. I'll probably do that at the start of next lecture, but that should get you through sapling for now.